Welcome to this lecture series in linear algebra. This is probably the last lecture of this module in which we will revisit the Cayley-Hamilton theorem. We have discussed this theorem earlier, but not in the form in which it is usually found in textbooks. But in this lecture, we will see it in that form. And we will be invoking a lot of things that we have been using in and out, like minimal polynomial and characteristic polynomial maybe at some point. Of course, we will use characteristic polynomial at some point. And other things that we keep using. So let me not recall a lot of things. If you know what is the determinant of an endomorphism, then you should be able to follow this lecture, assuming you are well versed with the discussions that have been happening. Okay, so let's proceed. So let's first discuss an operation on polynomials. It's a very simple one. Suppose we have this polynomial fx, which is defined in this fashion, and for concreteness, let us assume that we are working with the real number field. Then we write this to mean the polynomial where you just substitute x minus 1 in place of x. So to mean that thing, but once you expand this out, I don't know the formula. I think it's going to be 3x square minus 3x, I think. I could be wrong, doesn't matter. So this becomes x cubed plus 3x square minus x plus 0. Wow, this is 0. Yeah, okay. Interesting. Whatever, my computation may be a bit off. I don't want to spend time on it. So basically, this is a new polynomial which looks different from the original one, but is clearly a close cousin of the previous one. Any property, polynomial-like property of this is polynomial-like property of that. If you know the roots of those, if you know the roots of this guy, you know the roots of that guy. They are just translations of the roots of that guy. And similarly, we can talk about this polynomial, which is what you get if you write 1 minus x in place of x. And again, you expand this out, but this time you'll see that the leading term has a minus 1 rather than a 1. The leading term will have a minus 1 because of this minus x and the odd degree. So the monicness can get disturbed, doesn't matter. And here is a simple exercise for you. Show that if we have a polynomial px and some field element, then the original polynomial is irreducible if and only if the translated polynomial is irreducible. So I'll be referring to this kind of thing as a translation of the polynomial, although perhaps that is not a very good terminology. Okay, so I'm assuming you follow this, and now we can get to linear algebra. Okay, so this is going to be the main lemma that we need to establish. Suppose we have an endomorphism on a vector space V, and let's say lambda is in the base field, and mx be the minimal polynomial of t. Then this guy is the minimal polynomial of a kind of a translated version of t. You're sort of translating t by lambda, because you can't translate an endomorphism with a scalar. You have to put the identity matrix, or identity transformation, not the matrix. Yeah, and here this is just a sign term to make this guy monic forcefully. If m has even degree, then this was already monic, and this is a 1. But if m has odd degree, then this is not a monic polynomial. The leading coefficient will be minus 1. But this will take care of it and make it forcefully monic. So this is just an adjustment to make the thing monic. And so we will be showing that the minimal polynomial of the translated thing is translation of the minimal polynomial. That's the sort of thing that we are going to prove. And it's a very simple proof. You should do this yourself. But I can't just leave this as an exercise. So let mx be the minimal polynomial of lambda I minus t. And note that, or rather we know that, or I don't know how to say. So now mt is 0. Mt is 0 simply because mx was the minimal polynomial of t. So that is that. But this implies that this translated polynomial is satisfied by lambda I minus t. And this is just a check. You substitute in place of x, you write lambda I minus t. What you get is m of that, but that is m of t, because these things cancel out and this minus becomes a plus. So this is m of t, and that's it. M of t is 0, and this is satisfied by that. So we have the simple deduction. And now this gives us that the minimal polynomial of lambda I minus t divides m of lambda minus x, right? If this satisfies a polynomial, the minimal polynomial of this guy will divide that polynomial, right? So we have this this implication. And similarly, since this is 0, we have this guy is satisfied by t, clearly, which implies the minimal polynomial of t divides this polynomial. But the interesting thing that we need to do from here is just translate once, right? So just 1 second. Yeah, so what's going on? We have this division, and in place of x we can just write lambda minus x, and the division will not be disturbed. Simple exercise. So here if you write lambda minus x in place of x, you get x, and here if you write lambda minus x in place of x, you get lambda minus x. So now if you look at the blue things, the blue things give us, therefore capital Mx is equal to that, right? Because this divides that and the reverse, so this equality should happen, right? No, it shouldn't, because if they were both monic, then yes, then we could have immediately written that they were equal. But this may not be monic, as we commented. So the monic version of it is something that works. So this establishes a proposition. All right. So this has some corollaries. First corollary, I mean, this is a weaker corollary. We will actually prove a stronger one, but let's look at the weaker one. Fix an endomorphism and lambda be in the base field. And let's say px is an eigenpolynomial of t. Then this guy, where again there is a sign just to make this guy monic. So you translate the eigenpolynomial by lambda and adjust for the monicness. Then that thing is an eigenpolynomial of the translated endomorphism. Fairly natural statement, but a more stronger version is fix an endomorphism t, and let's say lambda is in the base field, and let's say p is the set of all the eigenpolynomials of t. Then this set, where you vary over the eigenpolynomials of t, and this particular translated and monicized version of them, this is precisely the set of the eigenpolynomials of the translated endomorphism. So it's a little bit stronger, or rather significantly more meaningful statement than the previous one. And the proof is very simple. We have, or let's say, the minimal polynomial of t, right? Where this is the saturation exponent psi, the highest power of px that divides the minimal polynomial. Okay, and we know by the previous proposition, by the previous slide, that the minimal polynomial of lambda I minus t. So I'm using this to denote the minimal polynomial of that guy. This is equal to minus 1 to the power degree of mx right? And now, what are the eigenpolynomials of this guy? Those are precisely the monic irreducible factors of the minimal polynomial of this guy. which is the monic irreducible factors of this guy. But what are the irreducible factors of this guy? Clearly, those are these people. And the monicized versions of them are these. So that's it. That's the proof. It was quite somewhat anticlimactic, but that's the proof, and that's a meaningful and important statement that we have on our hands now. Okay. So now we will prove something about the algebraic multiplicity. So fix an endomorphism again, and let's say Px is an eigenpolynomial of T. Fix an element of the base field, call it lambda. And for notation, let us write T lambda to mean the translated version of the endomorphism, and P lambda x to mean the monicized version of the translated eigenpolynomial. Then the algebraic multiplicity of P with respect to T is same as the algebraic multiplicity of P lambda with respect to T lambda. Right, P lambda is an eigenpolynomial of T lambda, as we just proved in the previous page. So this expression is meaningful, and this equality is what we want to establish. And this is nothing. So we have P lambda of T lambda is this thing, P of T, right? Yeah. And therefore, the dimension of the kernel, this is equal to dimension of the kernel of this thing, but that is same as the dimension of the kernel of, maybe I'll write one extra step which was not really needed. Forget about all of this. This is the dimension of V, degree of Px, right? Just agree with this. And this sign doesn't really matter. We can forget the sign, right? If this is a 1, then it's not doing anything. Even if this is a -1, doesn't matter. Kernel of, or rather the dimension of the kernel of -s, let's call this s. So the kernel of -s is same as the kernel of s, and that's it. So you can drop the sign, and what is the left side? The left side is the algebraic multiplicity of P lambda, and this is the algebraic multiplicity of P with respect to T. So that's it. So the algebraic multiplicities kind of don't change in some sense if you do the correct replacements. Okay. And now, finally, suppose we have an endomorphism and a field element lambda, and let's write this to mean the characteristic polynomial of T. Then the characteristic polynomial of lambda I minus T, so this just means the characteristic polynomial of lambda I minus T is a sign adjustment times the translated version of the characteristic polynomial of T. And this is just putting the pieces together of what we have done in this lecture. So write T lambda to mean the translated endomorphism. Let this be the set of all the eigenpolynomials of T, and for an eigenpolynomial, write or define P lambda x as the monic version of the translation of P by lambda. Okay, so then we know that this set is precisely the set of all the eigenpolynomials of lambda I minus T. And give me just 1 second. I think I made a typo somewhere. No, it's fine. Yeah, it's fine. So we have that. This is what we proved in the previous lecture. And now, not the previous lecture, I mean the previous slide. Now, q of t lambda, which is what we are interested in, is by definition of the characteristic polynomial that we gave, we have this is equal to p lambda x to the power the characteristic exponent. So this is the characteristic exponent of p lambda with respect to t lambda. But perhaps in the previous slide I should have noted that since the algebraic multiplicity of p is same as the algebraic multiplicity of p lambda, the characteristic exponents are also the same, because the characteristic exponent is just algebraic multiplicity divided by the degree of p lambda, but the degree of p lambda is same as the degree of p, and the algebraic multiplicity is same as the algebraic multiplicity of p. So the characteristic exponents are also the same. But anyway, this is what the expression is. So this is equal to, we'll just substitute the things here. This is equal to, or maybe let's do it slowly. So the characteristic exponents don't change. We can write that. And now this is equal to minus 1 to the power degree of p. Right. Here I should, so what I should be writing is a bracket, which is equal to that. Yeah, but this thing is equal to minus 1 to the power sum of the algebraic multiplicities, and then a product, very little space, very little space. I have to adjust somehow. So what am I saying? This thing, when you product it out, you'll see a sum in the exponent, and there will be a product over that. So use a different color to make things clear. So this is equal to minus 1 to the power this sum, and here we have a product, right? But this is nothing but the dimension of V, because sum of all the algebraic multiplicities is the dimension of the vector space. That is dimension of V. And here, if you look at the expression for the characteristic polynomial, this is nothing but q of lambda minus x. So the characteristic polynomial of t is just x in place of lambda minus x here. Just if we write an x here, that is the characteristic polynomial of t. But since there is a lambda minus x here, the above thing is equal to q of lambda minus x. And this is what we wanted to prove. That's it. So that proves that the characteristic polynomial of the translated thing is the translation of the characteristic polynomial, but with an appropriate sign just to make things monic. Okay. And now we can revisit the Cayley-Hamilton theorem. So if T is an endomorphism and lambda is an element of the base field, and if this denotes the characteristic polynomial of T, then the determinant of the translated endomorphism is Q of lambda. Okay, and now here we will use material from the previous lecture. We know that the determinant of T lambda, where what is T lambda? So T lambda is the translated endomorphism. And we know by the previous lecture that the determinant of T lambda is, you take the characteristic polynomial and evaluate it at 0 and with a sign, multiplied by the sign. So that is what we proved in the previous lecture. But we just showed that what is this guy? This guy is itself a sign and that thing. right? This thing is equal to that, which is nothing but q lambda here. And also these two things together become a 1, so all you get is q lambda, qt lambda. So it's a nice equation. The determinant of this guy is evaluation of the characteristic polynomial at lambda. And here is a corollary, but it's not truly a corollary of the previous thing. For any endomorphism, the characteristic polynomial of the endomorphism is the determinant of this guy. Now, an objection can immediately be raised here. We are thinking of x as a variable, whatever that means, whatever a variable means. We are thinking of x as a variable. So what does it even mean to take the determinant of this guy? This is not a matrix, this is not an endomorphism, this is not an n-tuple of vectors over V or anything. xi is not an object in our purview yet. X is a variable, I is an endomorphism. What does this even mean? Well, this is an endomorphism, so it's unclear what this object even is. But if you kind of pretend for the moment that x is an element from the field, then this equation makes perfect sense. That's what we have proved earlier, in the previous lemma. So I'm just saying that you can upgrade from here to there. One can do this, and since this object is not in the purview of linear algebra per se, we have to go beyond fields to even talk about it in a certain sense. One can get around all of that, but still, the correct way to do this is by going to rings and modules and PIDs, etc. So let me just say that this thing can be upgraded to that thing. And this is the Cayley-Hamilton theorem that is generally stated in textbooks. In the matrix language, it is a little less problematic to state it this way, but the matrix language makes little sense to me in terms of understanding. So anyway, this is the usual Cayley-Hamilton theorem, and we have almost proved it. When F is an infinite field, then one can in fact prove it with what we have done. But if F is just a finite field, there's a little bit of work that needs to be done here. But I don't want to do it. It's not really all that relevant. And yeah, with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time. Or no, I want to do some examples. So let's compute a few things. T is an endomorphism defined in this fashion. T of xy is that. Let's compute the characteristic polynomial of T by what we just learned. So to find the characteristic polynomial of T, we need to find the determinant of this guy, xi minus T. That is what we want to find out, right? That is the characteristic polynomial of T as we just showed. So how do we do that? We want to form the matrix of this guy, but the matrix of xi minus T with respect to the standard basis. So let's not write that. This is x times the identity matrix minus matrix of T, which is x and x on the diagonal minus, what is the matrix of T with respect to the standard basis? It is what I'm writing. And I think this is not the matrix I wanted to discuss. This might lead to some imaginary roots. Let's see. So this is equal to x minus 5 minus 2 and x minus 1. So that's the matrix. And what is the determinant of this matrix? Which is nothing but the determinant of xi minus T. That is what we are interested in. So this is equal to the determinant of this matrix. But that is, yeah. So immediately we can find the characteristic polynomial. Previously we needed to work a lot harder than this. But now with this formula in hand, it's so easy to find the characteristic polynomial. And that has applications because the roots of the characteristic polynomial are precisely the eigenvalues of the endomorphism. So now let's compute the eigenvalues of this guy. To find the eigenvalues of this guy, we just need to find the roots of the characteristic polynomial of t, which we just computed, which is x squared minus 6x plus 1. But the roots are, by standard formula, roots are those things, which is root 32. What is root 32? It's 4 root 2, I think, which is 3 plus minus 2 root 2. So those are the two eigenvalues of t. Again, previously we would work a little bit harder than this, but with that formula, it's so easy. All right, so now I really want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.